the first question I wonder is like, what was the path to, when you were training as a composer to being, such an early pioneer in kind of computer music?
Yeah, so um, I studied in Paris for 3 years after I did my military service during the Korean War. And I went to college, and then after college, I went to Paris to study with a famous teacher at the time, Nadia Boulanger. And I spent, basically 3 years there. And while I was there, I heard music that was in, intended for loudspeakers. Remember, in those days, all music that we heard was either TV music or music recordings of orchestras or chamber music or whatever, or bands where the intended source was not the loudspeaker. That that was the way they communicated. But when I was in Paris, I heard music by Stockhausen, where the intended source was the loudspeaker. And that was very exciting. I heard a piece by him called Contacta, which was based upon four channels, four uh, microphones on the corner of a square table. And they used a rotating loudspeaker in the center and put a single channel into the speaker, rotated the speaker, picked up, recorded the four output channels from the four microphones on a four-channel tape recorder. So that really got my interest. It was, and I imagined doing similar things, but maybe not just circular motion, but more extensive kind of spatial trajectories, distance and angle. And so when I finished my studies with with Boulanger, I went to Stanford to get a degree. They had no interest in this kind of music, and there was no interest in electronic music, tape music of any sort, which is not unusual in those days for an American university. But I played in the Stanford Symphony, and the percussionist next to me was a biologist. And of course, timpanists and percussionists, they have lots of rest, so we had lots of time to talk. One of the things that I talked about was the fact that I'd heard this music by Stockhausen in Paris. And one day she came up, 19, 1963. She handed me an article by Max Matthews at Bell Labs, his first publication of the idea of digital domain, doing music with computers. Of course, these were big, you know, batch processing computers. And so I read the article, contacted Max, and then he gave me a box of cards. So I had never even seen a computer before. My whole training was music. My interest was music. I was not a ham operator. I had no technological background. But in this article, there was one diagram which showed a computer, a digital analog converter, and a loudspeaker. And I thought, well, if I can learn to program a computer, then maybe I can bypass all the complexity of analog synthesizers that I knew about from Stockhausen's work at Cologne and Berio's work in Milano, others. And so I took a program course, learned to program, and that was the beginning. So I worked on spatialization beginning in 1964 at Stanford with long distance help from Max Matthews. And one of the tuba player in the orchestra, tuba players also have lots of rests in orchestral music. So he saw me at the, I knew him just as a tuba player, a really good one. When I brought this box of cards from Max to the computer center, he was standing there and he said, "What are you doing?" And I explained what I was trying to do. And he said, "Well, maybe I can help you." It turns out he was teaching TA for John McCarthy's course in Lisp or AI Lisp. So he helped me, taught me everything I needed to know to get going. And he basically became my angel. So in 1968, I had a fully developed spatialization program with Doppler shift through 4 channels, etc. But along the way, I discovered FM in 1967. And I was looking for a signal that would distinguish itself from the reverberant field. So a direct signal which has a little change in pitch will separate itself from the collection of reflections, reverberation, the echoes, and the direct signal therefore can be distinguished from the reverberant signals. And so I was experimenting with vibrato. I had studied, as a child, I had studied violin. Excuse me. And so I then just kept playing with vibrato deeper and deeper, faster and faster. And pretty soon I heard something that was surprising with 2 oscillators. I heard a complex wave that I knew would have taken probably 10 or more oscillators to reproduce. So that was the kind of moment when I realized, okay, there's something that's beyond the ear here. And so that's the whole beginning. That was the beginning of FM synthesis. So it was a musical discovery, an ear discovery. It was not a discovery of mathematics or engineering because I had no background there. And so I always like to point that out, that in all the years, my best tool has been my ear. It's the last thing that I rely on to tell me whether things are right or things are wrong. How does it sound? Which is perception. So a lot of my work had to do with, over the years, had to do with perception.
Did you say you when you learned the program, it was with John McCarthy?
Yeah. I took a course in Algol 60, which was in the day that was thought to be the language of the future. McCarthy was teaching Lisp because Lisp was his language. And we had a Lisp, we also had Lisp eventually at CCRMA. And I programmed some in Lisp, but the original language was Algol, and from that I learned the SAIL language, Stanford Artificial Intelligence Language, which was an Algol-like language with was, designed and implemented by the guys at the AI lab. So I was a early morning, late night user. I was not allowed to work during the day because I was not funded, but Dave Poole convinced McCarthy that this was an interesting project. And so over the years, music became one of the more interesting demonstrations that they gave at the AI lab, in fact. These super engineers, this was the Sputnik era. So the DoD gave tons of money to McCarthy and at Stanford and MIT, his colleague, forget his name, but anyway. So these were really the best of the best as far as computer scientists, engineers, speech. Raj Reddy, for example, at Carnegie Mellon, he was one of their researchers. And they taught me a lot. And I learned a lot from them. And but they really kind of watched as we built this quite extraordinary music system.
Well, that's amazing. That's an amazing person to learn from. McCarthy, also a hero of mine. Me and Nico got to see him speak in 2008, just a few years before he passed away. He obviously coined the term AI. I remember him saying that he just hoped that people continued to remember the importance of learning about logic in building thinking systems, which was a very affecting thing on me and Nico. That's very cool that you learned Lisp from him. I heard when you were at SAIL, you guys built the first online computer music system. What did that entail?
It was not real time, but it was a single pass system. But we had to write the output of the music program onto disks, and then when the computation was finished, then we recorded it from the disk direct through DACs, 4-channel DACs onto 4-channel tapes. So that was our system. Then eventually we got the Samson box, which was a real-time real-time signal processing computer, highly optimized for doing music. And the Samson box was probably produced more hours of music than any other single device ever until the DX7, maybe.
When you started experimenting with increasing vibrato frequency until you got to the point that you were producing, audio band interactions and complicated timbres, how quickly did you kind of realize the flexibility of that method?
Pretty quickly. It was a long night. I began and I had to wait for maybe 10, 20 minutes between each, say, 1.5 or 2 second sample, because this was a time-shared machine. So if the rate at which my samples were computed depended upon the number of users. But anyway, one of the things that I realized that at the end of this long night, I had made the deviation, that the depth of the modulation just made a linear change from 0 to big. So that meant that basically sweeping the modulation index, although I didn't know those terms. For me, it was frequency deviation or vibrato depth. In fact, that's the way I was thinking about it. Those were the terms in my head. So I thought, okay, vibrato depth from 0 to something, and what I heard was a diphthong, like ooh, which we know if we sweep the index from 0 to something 4 or 5, that's what the sound that we would hear. So I thought, well, this is amazing because there's no way anywhere on any device in those years where one could produce a diphthong, which of course is essential to speech.
Yeah.
And so then I developed the idea of resonances, like all these, the vowel resonances based upon Johann Sundberg's work. I developed a model for the singing voice, FM model. And that was very successful. And all of this, of course, was licensed to Yamaha back in 1972, 73. And they worked for what? The X7 was 1983. So they worked for 10 years before they had a real winning product. But they had foresight.
Did Yamaha consult you much as they were
Oh,
building?
yeah.
They did, yeah.
Yeah, I went to
Japan.
Japan maybe, I'm guessing maybe 8 or 10 times. And I would spend a week or two working with their engineers, explaining to them what I had learned. And they would listen to the changes I made on their real-time system, which was a PDP 8 or 5 or some small PDP computer with a breadboard implementation, but it was real time. At that time, we didn't have real time at Stanford. And so that was a lot of fun for me. And it was very interesting to be able to hear in real time and make changes. And that was pretty exciting. So they would listen and learn how I was hearing. So these engineers, maybe 50 or so over a period of 10 years, they're really the ones who are responsible for the DX7. I became the face of the DX7, and I always recognized them publicly that it was really about 100 really good engineers over a 10-year period to whom that DX7 should be attributed.
Once the DX7 came out, it was pretty rapidly adopted across the entire music industry. What did that feel like to just hear FM synthesis sounds just appear everywhere within like a year of that technology finally coming to market?
Well, that was not my world. That was all mostly pop music. And
right.
I didn't know much about it. But what I was very happy about was the fact that the DX7 democratized computer music. Until the DX7, you had to have a multi-million-dollar system, and but then the DX7 with one of the early Atari or Apple and the opcode system software, you had a pretty powerful workstation, and that's when Dave Bristow and I wrote a book about programming how to use the FM theory that was published by Yamaha. I forget the title exactly. I think it was FM Theory by Musicians for Musicians, something like that. And Jean-Claude Risset and I began writing a book about using, based upon the DX7 on perception, being able to demonstrate certain phenomenon, lots of phenomena. For example, missing fundamental phenomena, or resonances, all sorts of things that could be done. But then Yamaha in those days, they didn't, as soon as they had a new instrument, like, then they would stop support of the original one, DX7, the original DX7. So the people lost interest, and we never finished it, unfortunately.
I mean, I know that in the early days of computer music, especially with so many classically trained composers like you as early pioneers, there was a large emphasis on trying to reproduce the timbre of known instruments. But over time, it became increasingly a focus to also invent new sounds. Do you think when you first were working on FM synthesis early, a lot of your focus was on trying to reproduce sounds like, chimes that were hard to produce, with other methods? Or were you, as a classically trained composer, also interested in new sounds that you couldn't produce with other synthesis methods at the time?
Both.
Both.
Yeah. I mean, one learns a lot by trying to synthesize a sound that one knows well. For example, when you're succeeding, when you're close, and when there's something about the sound that's missing, so you have a target, and having a target made a huge difference. Jean-Claude and I both worked on synthesis of well-known orchestral sounds, just because we learned so much about perception, like the voice synthesis. That was one of the richest experiences of my life, was succeeding at creating female and male vocal tones, sung vowels. And because I learned so much about perception. But if you listen to my pieces, like Stria or Tyrannus, these are sounds that we'd never heard before. Boulez gave an introduction to Stria at the Théâtre d'Orsay in 1983, I think. And he said that there's nothing in this piece that I recognize from my tradition, but he really liked it. And so that transcription is of his talk is on my Karma website. So if you look at Karma, people, Chowning, you'll find a website, you find a lot of the Boulez's transcription. And it's a very interesting long commentary about Stria.
One question about Karma is, when you started Karma, was it always in that house up on the hill, or did it start somewhere else?
It started up on the old AILA. Yeah, and we moved into the current location on the hill on Stanford campus in 1986, I think, 85 or 86. But before that, we formed Karma in 1974.
Mm.
And we needed a kind of institutional independence from the music department, because we had grants from the National Science Foundation, and we needed a structure which didn't involve the typical kind of admin of a music department. So we decided to form Karma as a center, and the university deans supported it vigorously. And of course, we were making a lot of money at that point from income from the patent, most of which went into the endowment, which supported Karma's activities, and in fact, I think still.
I've heard that there's an old joke that Yale's science departments were always held back by being up on a hill. I remember when I took acoustics from Thomas Rossing,
Yeah.
I was always arriving at lecture out of breath because I'd be late and going uphill from half the campus.
Yeah.
You think that being up there filtered people who are serious about computer music compared to the rest of the department?
Yeah, yeah, yeah. It's you've probably put on a few pounds since then, right?
Yeah,
Yeah,
probably.
yeah. So we were all thin.
um, the DX7 reminds me of a question that we're always facing with, like when you're doing product engineering versus just inventing, there's always a trade-off between complexity and features and something that
Yeah,
actually can be adopted by the public. Today, we're trying to build bots that,
yeah,
small businesses can, talk on the phone for them, and these are not technical people.
right.
The DX7, I've only used an emulator of one, but it's very complicated to design the algorithms and understand what the effects are going to be.
Yeah.
I'm very curious, what was the push and pull between like complexity and being able to achieve really complex sounds versus something that was like simple enough that could be used in this like major Yamaha
Yeah.
consumer product?
Well, the cartridge had a very special attribute in that it was a read-write cartridge, and it would write in a few seconds. So what happened? People would plug in to write what they had done on this cartridge, would go into their pocket. They'd pass it to a friend who would copy it. The friend would end up in you know Singapore the next night and pass it to another friend who would copy it, and then that person would make modifications, and it would end up in Paris, 2 days later. And this was an amazing, amazing kind of metamorphosis of a single patch that would occur through time and through space, that really few people understood what would happen if you had, for example, 4 operators in a stack, and they all had different frequencies and different modulation indices and offsets. It was just too complicated. But there were some interesting sounds that were done, and they are preserved in these cartridges, and they were modified and used all over. The way I work is I have a basic unit of three modulators and 2 carriers, and the 3 modulators can be used to emulate resonances in the singing voice. For example, if you have the carrier frequency at 3 times the modulating frequency, and the modulating frequency is F0, the pitch frequency, then you get at a small index, you get a nice bump, filtered, looks like a filtered, you know, sawtooth wave or something. And so this is the way this is the way I build complexity out of using numbers of these piled on top of one another. So a single sound may be 4 or 5 of these all occurring together, each one contributing to another part of the spectrum. That's very easy to control. And so that's the way I build complex tones with FM synthesis.
If you were to emulate DX7 and you set the modulation index to max, do you know how far is it going?
How far is the
is the modulator shifting the carrier's frequency.
Oh,
Yeah.
The whole richness of FM is aliasing around 0 hertz.
Yeah.
That's the richness. So you get sideband components, the amplitudes of which are determined by the Bessel coefficients. But remember that the Bessel coefficients are nowhere present. They're a gift of nature. And the equation is so incredibly simple, and the explanations can be incredibly complicated, but nowhere is there a Bessel function present in the computer, but we need it to explain it. So when you have a waveform whose carrier frequency is well above 0 hertz, very simple waveform. For example, let's say you have a carrier frequency of 400 hertz, and you have a modulating frequency of 100 hertz and an index of 2. Well, you're going to have the carrier frequency at 400 and plus or minus 100. So we have something at 500, something at 400, at 300, something at 600, and something at 200, and probably a little bit at 100 and 700. So you get a nice sort of bell-shaped curve. Okay, that's with the carriers at 400 hertz. Well, now you move the carrier down to 100 hertz. So the first lower sideband is at 0. The second lower one is at minus 100. And the rule is sine of minus theta equals sine of minus theta equals minus sine of minus theta. It flips.
Yeah.
And it's 180 degrees and therefore adds to the carrier. So that's the whole richness of FM, this aliasing around 0 hertz.
As you said, you became the face of the DX7. Were you involved with the DX1 then and all through that?
The DX1 maybe was some form of it preceded the DX7, but they never released it. But they looked for a model that they could sell, they thought they could sell commercially. In fact, they way underestimated the number of sales they made, and they were back ordered for a year or so. And then they put out a DX1 and a DX5, I guess. Yeah. And then a lot of rack-mounted, DX modules. That one of the more powerful was the TX816, which was really powerful because you had eight of these. Was it 8 or 16 TX7?
I think it's 8. The one that we have is 8.
Yeah. So that was really powerful. And again, because you could build timbres by summing together the outputs. And Yamaha set up a Yamaha studio at Yamaha studio at IRCOM, and fitted out. And Dave Bristow was the manager, and I spent a year there working with David on various tones. But David had fabulous ears and keyboard skills. I had great ears, but no keyboard skills, because I was a fiddle player. But Boulez came up one day. We played for him a tone that was named Belwa. And Boulez listened, he said, I would have used that No, he said, of course you can use it, no problem. But then they were working on the predecessor of the 4X, and the engineering team said, no, we can't use off the shelf items, that's against, we're building our own expensive system. So they sort of made Les back down, and he couldn't. Interesting engineering politics.
I'm really curious what you're excited about now, what presently, anything.
Yeah, I'm working on a piece for Lisa Moore, who's a very fine New York pianist, for disc clavier. And because my hearing's not so good any longer. And this is a piece, I want the pianist just to have a real keyboard, because she's a concert pianist and specializes in new music, but she also plays the standard repertoire. But I want her to have the real action of the piano. But then I'm going to, because it's a disc clavier, you can mute it and turn off the acoustic sound. And at some point I will substitute an FM piano and then do things that have some unusual theoretical basis, which I would have to have diagrams to explain to you in a short time. But anyway, it's not so ear dependent. So it's something I can do, which is really exciting for me.
I know that obviously, you were very early as a musician entering the field of computer science before there was even a computer science department at Stanford. But I also know that a lot of, engineers and computer scientists are also musicians. Like I know Donald Knuth is an organist.
Yeah.
Was that a common finding, that there was a large amount of crossover at Stanford between, people that were musically inclined engineers and vice versa?
Yeah, sure. Remember, almost every kid, wanted to be a rock star, right? And so lots of engineers started with guitar or drums or some musical instrument. And so Julius Smith, who is our signal processing professor, who's got a PhD in EE from Stanford, he gets lots of students from engineering, because music is such a rich domain of application, lots of engineering problems. For example, source identification, separating out one acoustic signal from another, one voice, a soprano, say, from an alto. How you do that is a really tough problem. Just a signal processing problem and perceptual problem. So all of this music as a domain of application has brought lots of students over the years to working at CCRMA, which enriches CCRMA because they pass knowledge to the music guys music people who are working, etc.
When, you first were implementing FM synthesis, offline in a non-real-time manner, and then, eventually you said at Yamaha, they began to have a real-time version of it running in software. In the interim, there was a long, almost a decade between, those two periods. Was there motivation to try to reproduce those sounds using analog oscillators and muxes, or was it always a commitment to try to implement it using digital signal processing?
We never had an analog device in our studio.
Really?
Never, no. They were too unstable. And the whole richness of the DX7 and as a workstation was that you could reproduce exactly in one location because it was digital domain. And Buchla tried to make FM, but I explained that you can't do it because you're working in log space, changing voltage, and FM is based upon a linear space. So although he tried, it doesn't work. Simple, just plain and simple. It doesn't work. Plus the fact, if it did, it was so unstable you couldn't count on it being the same sound the next day, because the analog systems were so sensitive to changes in temperature, or primarily probably.
I think one last question I had is just that before the lectures, we've been playing relevant music from relevant to that topic. Do you have any compositions that are your favorite that maybe we could play before the lecture?
Well, Perennis is probably the piece that has been most played, and maybe good representation because it has spatialization. I mean, Stria, maybe it's not short. It's about 17 minutes or something like that. Whereas Tyrannus, I think, is 9 minutes, 50 seconds, just under 10 minutes. So I would say play Tyrannus.
This has been really, really cool to meet you and to hear these stories. Everyone at Gridspace and Noise Engineering, like we're all huge, fans of obviously audio technology and its history. And so, and I've, wanted to meet you since I was at Stanford. So it was very, very special. So thank you so much.
Yeah, my pleasure.
All right.
It's great to interact with people who care. We inspire one another, right?
Yeah, we try our best.
Yeah, that's the whole thing. Those who inspire become inspired and inspire others. Good.
All right. Well, thank you very much. Have a good afternoon and have a good 2025.
Thank you. And the same to all of you. Nice to meet you all.
All right. Thank you so much.